Welcome to this new session of the Al-Khwarizmi Applied Mathematics webinar. It is my great pleasure to introduce today a dear friend with whom I shared many wonderful moments during our PhD years at the University of Paris 6. Giovanni Peccati is a leading mathematician specializing in probability theory, stochastic analysis, and mathematical finance. He is currently full professor of mathematics at the University of Luxembourg, where he also serves as head of the Department of Mathematics and lead the research group revealing order in randomness. He obtained his master's degree and PhD in mathematics from Sorbonne University. Before joining Luxembourg in 2010, he held academic positions in Paris, including appointments at Sorbonne University and the University of Paris-Nanterre. Professor Peccati is internationally recognized for influential contributions to Malevin calculus, Stein's method, normal approximation, and stochastic analysis on Wiener and Poisson spaces. In 2018, he was elected the fellow of the Institute of Mathematical Statistics in recognition of his seminal work in this area. His research connects deep theoretical development with modern applications in high-dimensional probability, stochastic geometry, random fields, and machine learning. He has authored numerous highly cited papers and co-edited important referees works, including the book Stochastic Analysis for Poisson Point Processes, Spring 2016. Beyond research, he is deeply involved in mathematical leadership and outreach, notably serving as president of the Luxembourg Mathematical Society. Dear Giovanni, thank you very much for accepting our invitation, and the floor is yours.
Okay, thank you very much, Rafik, for the invitation. Thank you to the organizers. It is a great pleasure for me to give a talk at this prestigious series of webinars. And so today my talk will be about, let's say, the large-scale analysis of neural networks. So I will tell you what a neural network is for me, that I will look at as probabilistic objects. And I will explain to you how it is reasonable to think about them as probabilistic objects, in particular about as random fields later on in my presentation. So my presentation is based on two works. So there is a work from a couple of years ago co-written with Stefano Favaro, Boris Hanin, Domenico Marinucci, and Ivan Nourdin. And then a more recent work with my PhD student, Lucia Celli. You will see the name of Lucia appear in other places because she developed more results since last year, the year when this paper was written, until now. So there are more papers from Lucia that I would like to discuss a tiny bit during my presentation. So I will move then to my first slide, which is, let's say, an informal description of what a neural network is for me. So what I'm going to look at during my presentation is a very specific family of neural networks that one can see as the basic building blocks, or more general, what we call architectures of neural networks you find real life in your everyday life. And so these are called fully connected, feed-forward deep neural networks. So I will refer to them as fully connected neural networks. So these are functions that are parameterized, so they depend on a bunch of parameters that are somehow biologically inspired, and that go from some input space, let's say of dimension capital N, some output space of dimension capital N. And these functions are recursively defined in a way that as a sort of juxtaposition of layers of computational units that we call neurons. So I will tell you more precisely a definition of a neural network in my next slide, but the basic idea is that each layer of computational units that compose the network takes the output of the previous layer as an input, and then it applies to this input non-linear transformation first, and then an affine transformation, in such a way that one can represent this neural network as a long chain of alternating affine, nonlinear, affine, and nonlinear transformations. So in my picture, each layer is represented as a column. So the first layer is always the input of the network. The last layer is always the output of the network. And then every layer which is in between is customarily called the hidden layer of the network, right? So in our case, there are two hidden layers, the red one and the deep green one. Now, what I would like to point out immediately is that in my description of the network, there are two dimensions that play a crucial role and that are going to play an important role in my presentation. So one dimension is what we call the depth of the network, and I'm going to denote the depth with the letter capital L throughout my talk. And the depth of the network is the number of hidden layers. So it is the number of layers minus the input and the output of the network. And in my picture,
please, can you explain again the difference between hidden layer 1 and 2, please? What is the difference between them?
Oh, you will see later on. But so what basically, you have to read the picture that is here from the left to the right.
Okay.
And informally, this picture means that given an input, this input is transformed by a first layer of computational units, which is this red one.
Okay.
And then this layer of computational units is used as an input from the next layer, which is the deep green one. And then the deep green one is used as an input by the last layer that gives you the output of the network, right? So so you have to read from the left input to the right output, and then each column should be seen as a layer of computational unit that transform in a certain way the previous input, right? So the depth of the network is therefore the number of layers that stay between the input of the network and the output of the network. There are two of them in my picture. And then there is another dimension, which is the width of the network. And this is the maximal size of the hidden layers. So here the hidden layers have dimension 3, the first one, dimension 3, the second one. So for us, the width of the network is given by 3, right? And most of the analysis that I'm going to perform will concern the behavior of the network, seen in a certain sense as a random object, whenever the depth of the network is fixed or grows very slowly, and the width of the network diverges to infinity. That is, one adds more and more dimension to each of the hidden layer, which is inside the network itself, right? So this is what we call the infinite width regime, and this is what I'm describing here. Okay, so this is a sort of schematic representation of this network. And now I'm going to move towards a formal definition of what is going on. You will see why it is fitting to say that the network is defined recursively, and you will see how this representation as graph is fitting to the formal definition of the network itself. And so, by the way, the fact that this graph representation is given by connected graph simply indicates the fact that each coordinate of each layer contributes to the value of each coordinate of the subsequent layer, right? So they are connected in this way. Now, more formally, so this is the formal definition now that I'm going to give you, right? So I'm going to consider, therefore, a network with a fixed depth, capital L, which is fully connected, right? And this is a mapping that I'm going to denote by ZL plus 1, right? L plus 1 is let's say, is the number of the layer corresponding to the output that goes from some input space of dimension n0 into some output space of dimension nl plus 1. So it takes a value x from Rn0 and it transforms it into a vector of dimension nl plus 1. Now, the recursive definition of the network works as follows. So it's quite easy to understand. You take the input, which is point x living in Rn0, and the first layer of the network simply takes the input and applies to it an affine transformation, right? So this affine transformation is given by two objects. One object is the translation parameter B1, which will be of dimension n1, and so which is a vector living in Rn1. And then there is a matrix W1, which has dimension n1 cross n0, right? So this first layer, therefore, takes an input of dimension n0 and transforms it into an object of dimension n1 by applying an affine transformation. B1 is a vector and W1 is a matrix. Now, the crucial point is the behavior of the second layer. Now, the second layer takes the output of the first layer, which is defined as Z1 of x, and applies to each coordinate of the layer a non-linear transformation, which is sigma of x, denoted generically sigma of x, but that in many applications or real life situation is very often given by the positive part, the maximum between x and 0, which in the literature is called very often the rectified linear unit. Or you can think about sigma of x as a very smooth transformation, sigma of x, right? So whenever I write sigma of z1, so sigma is the mapping from R to R, and sigma of z1 is the object which is obtained by applying coordinate by coordinate sigma to the coordinate of z1. And then the second layer takes the sigma z1, which is an n1 dimensional object, and applies to it another affine transformation with vector b2 of dimension n2, and then a matrix w2 that acts on sigma 2 and transforms this whole business here into an n2 dimensional object. And then this goes on, so on and so forth, until the last layer. So each layer L takes the output of the L minus 1 layer. It applies to each coordinate a sigma transformation, which is, for instance, the rectified linear unit of the tangent or this very smooth kernel like hyperbole, the tangent here. And then it applies to it an affine transformation. And then until the last point, L plus 1, which is the output of the network, right? So the components of the matrices have names. We call them the weights of the network. And the components of the vectors B1, B2, BL plus 1 that define these affine transformations are called the biases of the network. And if you put everything together, the weights and biases, you obtain what one calls the trainable parameters of the network, meaning that these are the parameters that we are going to try to optimize in a certain sense that I will make clearer later. So the collective collection of the weights, that is the entries of the matrices, and the biases, that is the entries of the vectors B that compose my recursively defined neural network, will be indicated as theta 0. Right? So theta 0 will indicate the collection of the parameters that define our network. Right? So this is the formal definition. And my previous image is just a stylized, schematic description of this way of representing the network recursively as an alternate application of affine and nonlinear, affine and nonlinear transformations. And now, if you go back to my previous image and we take into account this formal representation as a network, as a recursively defined mapping, so we end up with my third introductory slide that tells you that now if you define by A of L the affine transformation of the Lth layer, and you take into account the recursive application of the nonlinear, what we call activation function sigma, then my neural network is, as I was anticipating in my very first slide, simply a composition of affine mappings, nonlinear mappings, affine mappings, nonlinear mappings at the last level, AL minus 1, right? And so one remark that I will make is that the affine transformation changes from layer to layer, right? Here we have one affine transformation, which is different from the second one, which is different from the third one. But the nonlinear transformation sigma stays the same for every layer. So there is no mathematical fact that forces us to do that. It is simply the classical configuration of the network. It has been observed that changing this nonlinear activation function sigma from layer to layer doesn't change the performance and the behavior of most networks in a significant way. And so typically we consider this sigma as being a fixed one, right? And so, yeah. So this is my definition, right? So this is parameterized, recursively defined function. Now, how does, just in one slide, how one does use this function, and why can we identify this function with a probabilistic object? For the moment, everything is deterministic. So the classical, typical, standard, most simple way with which we use neural networks of this type, is to approximate, that is, to use the network in such a way that it approximates some unknown function that goes from our input space into our output space. And the approximation means that we want to put forward an optimization procedures that allow us to move around the weights and the biases, what I called the trainable parameters of the network, in such a way that at the end of the optimization procedure, the network behaves as some unknown function that we want to reproduce from our input space into our output space. And the way of doing that, I mean, the typical standard vanilla way of doing that, is to start with what we call a training data set. So a training data set is a collection of points, k is the number of the points, in which one is given an input, xj, coming from our space, and then the true value of the function we would like to approximate on that space. Think about S as a label, for instance, as xj is an image. So this is a collection of points that tell you that for an image representing, I don't know, either a cat or a dog, fx of j represents the label cat of dog, etc. You would like to reproduce this function. And our goal, the typical goal, is that of adjusting, and when I mean adjusting, I mean optimizing. And when I say optimizing, the right jargon is to say to train the network, is to optimize the weights and the biases of the network in such a way that the network not only behaves as the unknown function fx on the training data set, which is not in general very exciting. That is, in that case, this would mean that the network only learns the labels that were fed to it before, but also that it behaves correctly as the function for inputs that are outside the training data, what we call the out-of-sample performance, right? And this is the amazing feature of this network, is that you can train them not only in order to reproduce the good performance of the function within the training data set, but also outside the data set. And the optimization procedure that is put forward, that is used in order to train the network in this sense, is fundamentally composed of two steps, and then many, many others that I'm not going to describe. And the first step is the one that allows us to think about a neural network as a random object. And what happens is that the right way of starting the optimization procedure of the network is that of randomly initializing the parameters. That is, to choose the weights and the biases of the network in a random way, according to some distinguished, and it will be spoiler, it will be the Gaussian distribution, distinguished multi-dimensional probabilistic distribution. So therefore, the optimization procedure is composed of two parts. So first of all, we randomly initialize the parameters of the network, and then we optimize, starting from this initial random value of the network, we optimize the weights. And in order to optimize the weights, one does the typical thing, that is that of minimizing some empirical loss, like this squared empirical loss that I put at the bottom of my slide. And by, for instance, by using some variant of gradient descent. Right? So we use some variant of gradient descent in order to minimize this loss. And if you read this formula, this loss simply tells you that we are taking the sum over all the points in the training data set of the L2 discrepancy squared between the true label, the true value of the function, and the value which is predicted, or let's say, or which is given by our neural network. Then you see this as a function of the parameters, and you optimize this as a function of the parameters. Now, there is one important point that has to be put forward, is that by construction, that is, because of this recursive definition of the network, this problem of optimization is highly non-convex. And in particular, if you look at the internet, descriptions of the loss landscape, that is the collection of the minimum of this function that you're trying to optimize, you will see that geometrically, this loss landscape has a completely different form as the loss landscape, which is associated with the convex optimization problem. And there are a number of local and non-local minima that are spread out in a sort of geometrical and non-trivial way. So the fact that this optimization can happen at such a level of performance is still not completely explained mathematically, at least to my knowledge, at least considering my knowledge of the state of art about this kind of questions. But in any case, this is the way in which the optimization is performed. And now, since we have a function that goes from an input space into some output space, that depends on weights and biases. And since these weights and biases are chosen at random, then de facto, my neural network becomes a random function. That is, a random field, if you want to use a term which is closer to what we use in stochastic analysis right now. So it becomes a random field, which is obtained as a very non-trivial, non-linear iteration of affine and non-affine transformations of some collection of random parameters. Now, there are several ways of initializing at random a neural network. The one that I'm going to choose is referred to, so I didn't write this, as the Lecan optimization. So I think you had a talk by Lecan a couple of weeks ago. And this way of initializing is the following. So we are going to choose at random, as I was saying, both the entries of the matrices that define their affine transformations and the vectors, or translation vectors, if you want, that define the same affine transformations. So the weight, everything is chosen to be independent. So every entry of the matrices is independent of the other entries of the matrices, and all the matrices and vectors are independent. Everything is independent, and everything is an independent Gaussian random variables. And so what one does is the following. One chooses the entries of the matrices as center Gaussian random variables that are commensurate by common constant C of W to 1 over the size of the previous layer, NL minus 1. Now, if you write these affine transformations in coordinates, this is exactly the same normalization you would use in the central limit theorem, fundamentally. You are normalizing, so if you write this affine transformation as sums written in coordinates, then this basically means that you are multiplying the sum by 1 over the square root, the number of summands. So this is the same normalization you would use in the central limit theorem, fundamentally. And on the other hand, the biases are just Gaussian random variables that are centered and have a common variance, C of B. So I'm allowing C of B to be 0, which means that I can take purely linear transformations, so I can forget about this, and basically the theory applies to that. And also what I'm going to look at, to impose and to assume, is that my activation function sigma is a fairly regular function. That is, I'm going to fix an R, it can be 0, and I'm going to assume that sigma is a function of class CR, so it's continuous with continuous derivative up to the order R, with an R+1 derivative that exists almost everywhere, and which is polynomially bounded in some sense. They're polynomially bounded. So in particular, if you choose R equal to 0, this configuration covers the case of the positive part, which is a C0 function. It is continuous with a first derivative that exists almost everywhere. So except for the origin, it exists everywhere. And it is, of course, polynomially bounded. And these are truly the two cases you might keep in mind. You might keep in mind sigma to be the positive part, or you can take sigma to be a very smooth function, like a sigmoid function, a function of class C infinity, which is bounded. These are truly the two cases that are going to play a role. And everything else is just more bookkeeping and maybe more technical considerations, right? Now, okay, so now we have all this in mind. And what I would like to look at is what happens to my network once again, whenever I keep the number of iteration in my recursive definition fixed. It is, I'm going to take the depth of the network to be fixed. And whenever I let the size of each one of the hidden layers of the network diverge to infinity. And in order to simplify everything, I'm going to assume that each one of the layers, the hidden layers of the network, are going to diverge to infinity at the same rate n. So you can even imagine that each one of them is exactly equal to n. Actually, it's a good idea to think about that in order to simplify your interpretation and reading of the formula, right? So I'm fixing the number of iteration of this recursive iteration of the network, and I'm letting, let's say, the dimension of this, of the image of the affine transformations that are inside the network diverge to infinity at the same rate. So I'm taking matrices, weight matrices W, that become larger and larger, And also I'm taking biases, BL, that becomes of larger and larger dimension. But I'm not moving the number of iterations, and I'm not moving the dimension of output and not the input of the network, right? So I'm just fixing. So if you visualize, as I did before, as a graph, so this graph is fixed in length. The entry point, which is this blue part and this yellow part, stay fixed in dimension. And what I'm going to do, I'm going to let the size of the number of blue dots and the number of deep green dots diverge to infinity, right? And this is what is called the infinite width regime of the network. And I'm really looking at this as a random function right now. And I'm looking at what happens to this neural network whenever this little n dimension diverges to infinity. Now, whenever one does something like that, whenever one lets this little n width go into infinity, there are two phenomena that take place. And these two phenomena are tightly related. And let's say now they're very well understood, and there are other challenges that are important to understand at the level of neural networks. But let's say maybe 5 or 6 years ago, this kind of phenomena were truly a breakthrough in our understanding of how neural networks behave. So the first phenomenon is described in this slide. It is called the neural tangent kernel phenomenon, or the neural tangent kernel regime. And basically, in a sort of a quick way, this phenomenon that dates back to a historical paper by Jacotte and other authors from 2018 tells you the following. So if you let the width of the network, that is, you let the network increase in the width dimension, and you let become this width dimension very, very large, then with overwhelming probability, that is, with a probability that converges to 1 exponentially fast with n, training the network, that is, optimizing the network, is indistinguishable from the fact of training a linearized version of the network. What I mean by that is that with overwhelming probability, if you want to train a network where n is very, very large, then what you can do by obtaining fundamentally the same result is to train a network where you have replaced the network itself by its first order Taylor expansion as a function of the parameters. That is, you are replacing the network itself by what the first order Taylor expansion, which is expressed in this formula, where nabla of theta represents the derivative, the gradient of the network is a function of the parameters, right? So this is the first order Taylor expansion. And this is an incredible, powerful message because it tells you that at the end of the day, if you take the width to infinity, then you can transform your highly non-convex optimization problem in a standard optimization problem, right? That is in a convex optimization problem, because now you are optimizing a linear model, and if you try to optimize, to minimize the square loss, you fall squarely into a convex optimization problem, which is well understood. And not only that, one also knows that once one has an convex optimization problem like this one, then everything about the training is determined by a kernel that can be associated here to the gradient. This kernel is called the neural tangent kernel, and it is simply given by the mapping that is obtained by taking the scalar product of the gradient of the network at different points. And so this NTK, neural tangent kernel theory, tells you that this kernel becomes deterministic and becomes large, which means that everything is completely determined in the training of the network, and everything depends deeply only in the initialization of the network, right? So this is the first phenomenon that takes place. The optimization becomes basically the optimization of a linear model with a kernel that becomes deterministic in the infinite width limit. And now the second phenomenon that for deep reason is tightly connected to this phenomenon tells you something absolutely crucial for the behavior of the network in initialization, right? Remember, so the network is a parameterized collection of functions, and now we chose at random the parameters that define the function, and now we let the width of the network is one of the dimensions defining the network diverge to infinity. Now we have defined everything in such a way that the salient normalizations are consistent with the central limit theorem, And therefore, probably, not unexpectedly, what happens is a functional central limit result, right? So what we have is that if you let the width of the network diverge to infinity, then your neural network itself, without any further normalization, every normalization is contained in the way we have chosen at random the weights and the biases of the network. So this object, which is a non-linear transformation of a Gaussian collection of parameters, so this ZL plus 1 is a non-Gaussian object, converges functionally to a multidimensional Gaussian process with independent components. And this Gaussian process is some limit covariance, which is defined recursively in a way that reproduces the recursive definition of the network, right? So we have KL plus 1, which is the limiting covariance at the level L plus 1, is defined in terms of some transformation involving sigma of a Gaussian field that has covariance KL, and the first covariance K0 is given simply by this formula, which is C of B plus CV over N0. So CB is the variance of the biases, CW is the variance of the weights, and this is the scalar product with X and Y, right? So this recursion can be solved sometimes cannot be solved. The only information which is important for us is that recursion ensures that fundamentally the Gaussian process that is here inherits the regularity property of the activation function sigma. So in particular, if sigma is continuous, your process will be continuous. If sigma is Lipschitz, the function will be Lipschitz. If sigma is smooth, your Gaussian process at the limit will be smooth, etc., etc. Now, I have put some simulation here. On the left-hand side, you have a simulation of the neural network, which is this random field. And on the right-hand side, you have a simulation of the Gaussian limit. And I started with very low values, the width, which is equal to 8 here. And you can see, and I choose sigma to this to be the rectified linear unit, which is the positive part. And you can see here in the simulation that the fact that the sigma function is a piecewise linear gives you samples of your network that have some sort of piecewise linear components. And then in my next slide, I will just propose to you other simulation. This is for a network of depth 2. There are 2 hidden layers. I will propose other simulations of the Gaussian process at the limit on the right. And this is a simulation of the neural network for n becoming larger and larger. So we have 64 here. We have 256, 1024, 496, etc., etc. So there is nothing particularly striking between the 2 pictures on the left and on the right. They're not coupled in any way or form. They'll be sampled in a sort of independent way. So there is no connection between them. And it is just a way of representing different shapes, possible shapes of the network at different levels. Okay, so this is the functional central limit theorem. And now I would like, so so this is the point, more or less. This is the state of my knowledge in 2023, when I started thinking about this kind of problems. And then in 2023, I thought, okay, yeah, machine learning is doing a lot for me already. So what can I do for machine learning? And what can I do for machine learning is to look at this kind of central results that are here, that are particularly relevant, in particular in the light of this MTK phenomenon, and to try to provide, let's say, quantitative versions of results of this type. That is, we have central limit theorems. We have in particular one relevant central limit theorem here. And I would like to, and the kind of results that we have been developing, on which this talk is based, are results that allows us to quantify the speed of convergence to the Gaussian limit that is put forward in this theorem. And so, and by the way, the theorem was proved in some probably limited form, but already very relevant in 1996 in a foundational paper by Radford Neal, right? And we are going to look at those, right? So the kind of questions I'm going to ask are questions that concern how fast, and so in which way we can quantify, similarly to the Berry-Yassine theorem, the convergence to Gaussian of this kind of central limit theorems that I would put forward here. Now, let me tell you some assumptions, some results, let's say some features or some properties of the neural networks that are crucial for us. So first of all, if you think about it, the neural network is is recursively defined in such a way that each layer of the network is transformed in some nonlinear way, and then there is an affine transformation with Gaussian weights that is applied to it. And if you remember one of the very first, so this slide here, you see that the last operation which is done on the network on this sequence of inputs and outputs is to apply one final affine transformation. And we know that this one final affine transformation is of the Gaussian type, right? So the vector B and the matrix W is respectively are Gaussian vector and a Gaussian matrix. So this means in particular that it's not difficult to convince oneself that if you condition the network at the level, so the output of the network, if you condition to all the previous layers except the last one, which is what I wrote here, then the object you have is a Gaussian object. That is, these neural networks are by construction conditionally Gaussian objects with a conditionally Gaussian random matrix, covariance matrix, that is given by an expression which is completely explicit and that I wrote in this first formula here, right? So one doesn't have to memorize this formula, but just the idea that these objects are all conditionally Gaussian objects. Now, from the standpoint of stochastic analysis, this tells us something important, that is, if you now condition on this random covariance matrix sigma of L, you can actually observe in a sort of a very direct way that this covariance, for instance, if you limit this covariance to a finite number of inputs, x1, xn, so this becomes a matrix, and this matrix acts or has a function with respect to the vector, corresponding vector of the output of the network, that is described from the standpoint of stochastic analysis, the Stein's kernel. That is, if you condition on the previous, let's say, on the layers that precede the output layer, then you can prove that let's say that this matrix S determines an integration by parts form. That is, if you take the expectation of Z and you multiply it by the gradient of some test function phi of Z, then this is equal to the expectation of S, which is this random covariance matrix, inner product in the sense of Hilbert-Schmidt norm of the Hessian matrix of phi computed in the vector Z, right? And if S is deterministic, if S was deterministic, this will be the usual integration by parts formula, which is obeyed by the multidimensional Gaussian distribution. Now, the fact that one can single out so easily a Stein's kernel, that is a random object that forces the vector Z to obey an integration by parts formula, fundamentally puts into the game a collection of techniques that I've been using a lot during my life as a scientist, that is called the Stein's method. So Stein's method is fundamentally a collection of results that tell you that if you can prove that a certain vector verifies a sort of approximate integration by parts formula, then you can measure the distance between the distribution of the vector and that of the Gaussian random vector by measuring how far this sigma is from a deterministic covariance matrix. So basically this object here, the Stein's kernel, the closer the Stein kernel is to a deterministic covariance matrix, the closer the distribution of Z is to a Gaussian distribution. And actually, if you take this standpoint, you can say confidently that the central limit theorem that I was describing before, the one by Radford-Neal, originates analytically from the exact fact that this matrix sigma of L, which is the metric, the covariance metric of random covariance metric of our field, converges towards the deterministic matrix, which is a limiting matrix of the Gaussian object. And this convergence, the convergence of this random matrix to this deterministic matrix of the limit, is tightly connected. It's basically the same phenomenon as the NTK phenomenon, and one can discuss about that. And then finally, what I would like to point out once again is that this, because of the assumptions you are making on this function sigma, then my random field ZL plus 1 lives in good spaces of functions. That is, it lives in some sort of Sobolev spaces of random functions, and we are going to exploit that. Okay, so let me go on. now. So these are the salient features. And now what I would like to point out is that we are going to try to measure the discrepancy between the network and its Gaussian limit fundamentally in two ways. So first of all, we're going to do that in a finite dimensional setting. So finite dimensional setting means that we're going to take a finite number of inputs and we're going to measure the distance, the probabilistic distance between the restriction of the network to this finite number of inputs and the restriction of the Gaussian limit to this finite number of inputs. And the way we are going to measure the discrepancy between these two objects is by using a very strong distance, which is the total variation distance. So given to vector x and y, the total variation distance between the distribution of x and y is given by the supremum over all Borel set of the probability that x belongs to C, so all Borel set C, and the probability that y belongs to C, right? So this will be our first result. And our second kind of result will be a bit more ambitious in the following sense. We are going to try to couple as random functions, not as random finite dimensional objects, but as random functions, the two fields ZL plus 1 and GL plus 1 on the same probability space. And then we are going to try to measure the discrepancy between the distribution of ZL plus 1 and GL plus 1 as random functions that live in a subole space, so as genuinely infinite dimensional objects. Now, what we have that ZL plus 1 is a conditionally Gaussian object. That is a Gaussian object with a random covariance, a random field with a random covariance. And GL plus 1 is a Gaussian field. Now, how can we couple a conditionally Gaussian object with a Gaussian object on the same probability space? So we didn't try to be particularly original in our paper. So we did it in the same way in which you would couple two random variables, two Gaussian random variables, let's say on the same probability space. We have two Gaussian random variables with two distant variances. How would you couple them on the same probability space? You take one common n01 random variable and you multiply this n01 random variable first by one variance and then by the second variance and hope you have obtained your coupling. So we did the same here in a multidimensional setting. So we studied this trivial coupling between the random field and its Gaussian limit. So we took the square root of the random covariance, convolve it with the common white noise, and then we take the square root of the limiting Gaussian object and convolve it exactly with the same Gaussian noise in such a way that the white noise here is independent of the random matrix that is here. It turns out that this coupling is not far from being the optimal one. So we have good news, it works very well, but the idea is a very simple one. And in particular, one can prove that if one looks at Z and G, or the coupling Z tilde and G tilde as random object with values, for instance, in a Hilbert space of subole of Hilbert space, like W2 of Q, then this expectation, so the expectation of the squared discrepancy in this sense, can be written as the expectation of the squared Hilbertine norm of the difference between the square root of the two covariances. One is random and the other one is not random. Now, this is what we did. And so I have a modular talk, which means that I can tell you the results. And then in the 5 minutes, I guess I have, so I asked for confirmation. I think I have 5-6 minutes more. I will tell you some idea about the proofs of the results. So the results that we have are the following. So I have 5-6 minutes, right?
Yes, 6 minutes.
Yeah, fantastic. So the first result is a finite dimensional one. And so this is a result that has been refined very much with respect to its initial version in this common paper with my student. And this result tells you the following. Now, suppose that you do something which is even more ambitious than that. That is, you consider the network, you fix a finite number of inputs, and not only you look at the value of the network on this finite number of inputs, but also you allow yourself to take derivatives. That is, you take a vector that at each coordinate has the value of some derivative of the network computed in x1. Right? So you can take J1 to be 0, in which case we have the value of the network, but truly allow ourselves to also take derivatives of the network because we know that the network is smooth enough. And our result is that the total variation distance between this vector of derivatives and corresponding vector of derivatives of the Gaussian limit goes to 0, and the total variation distance is 1 over n multiplied by some absolute constant. And the good news is that this bound is optimal. It is, we have a matching lower bound. And this result requires that there are some sort of non-degeneracy assumption, which is a standard one at the limit, but one can also get rid of this degenerate covariance. You can also get rid of this and deal with degenerate covariance structures. So, and this result is a multi-dimensional results. In the one-dimensional case, we obtained it already in our original paper published in 25, but written in 2003. But in the more general cases, multi-dimensional case, the only available bounds were of the order 1 over the square root of n, or there were similar bounds or order 1 over n, but in transport distances. So in the total variation distance, this result was completely new and optimal. Then there are some developments of this kind of theory in 2 further papers by Lucia. One is about a non-Gaussian situation in which the weights are non-Gaussian, and the other one concerns Edgeworth expansions. Now, what I would like to point out is that the speed of convergence to 0, which is 1 over n, is independent of the architecture of the network. It doesn't depend on L, it doesn't depend on sigma. It's a sort of the absolute speed of convergence, which is some sort of a universal speed of convergence. And this is some relevance also towards some applications, for instance. And now, the second result is the functional one. And the functional one tells us the following. So now suppose that the eigenvalues of the covariance of G converge to 0 fast enough in such a way that their square root is summable. Then in this case, the discrepancy in the sense of subless spaces goes to 0 at a rate 1 over n to the power 1/8. And this n over 1/8 can be moved from the subless space to the Banach space of continuous functions in case where the sigma is smooth, that is of class C infinity, right? And once again, this rate, 1 over 8, is a rate which is universal in the sense that it doesn't depend on the architecture of the network. Now, this assumption here that the eigenvalues of the covariance of GL plus 1 are summable in this sense might seem strange or analytically difficult to prove, to deal with, but it is actually not the case. So for instance, we know that if one take sigma to be the positive part, then this summability is automatically verified whenever one restricts oneself to the sphere. So this is a paper by Betti and Bach. And we also know from one of our papers for 2023 that if you take sigma to be smooth, then this summability assumption is always verified, right? And what we have here now is a simulation. So this is this ReLU field. So on the lower part of the picture, you have the limiting Gaussian field. And on the upper part of the picture, you have the neural network with the width n. And the two of them have been coupled, as I was telling you before, right? Have been coupled by being convolving the square root of the covariances with the common independent Gaussian noise. And as you can see, as n goes to infinity, the restriction to the sphere of my network is going to converge very convincingly to a version, to something which is very close to the limiting Gaussian field. So yeah, this is the final picture. And okay, so I will skip this and I will go, and this is a demonstration of the theorem, let's say, of the speed of convergence for a field which is with a smooth time H activation function. And here you have the Gaussian field, its first gradient and something, and this is the network at the width 100 and then 1000 and then 2000, 3000 and then until 4000, and you see that basically both the field and the gradient that are coupled as before are very close one to the other, at least in the simulations. So very quickly, what kind of techniques we use? So in the finite dimensional case, we use some very strong estimates that are due to Boris Hanin, and we fundamentally use, in the one-dimensional case, some version of Stein's method, as I was anticipating, and in the multi-dimensional case, we use entropic techniques that truly are very much the let's say, the fruit of the labor and of the immense talent of my PhD student Lucia Celli. So we managed to use entropic information type techniques. And on the other hand, at the functional level, we had really to overcome a problem that tells you that if you consider this quantity, the square root, the Hilbert-Schmidt norm of the difference between square roots of covariance functions, this object here is truly not amenable to analysis in any possible sense. And in order to do that, we look in the literature for inequality that's allowed to get rid of the square root. We couldn't find anything of value. And at the end of the day, we ended up using our own estimate that I would like to praise a bit. It's an estimate that allows you to pass from square root of differences of covariances towards covariance in themselves once you can control the trace of the matrices. And these terms that involve traces are the one that explain the fact that we have this trace condition with the sum of the square root of the eigenvalues. And this was a technique that we used already in some studies about random fields in a completely different setting. And so I will finish with a thank you for your attention and with a very restricted list of references. Thank you very much again.
Thank you, Giovanni, for this nice talk. I start by a general question regarding slide 6. Yes, slide 6, yes.
Yep. Let me go there.
Okay, assumption, yes.
Yeah.
You assume that the Gaussian processes are centered. Is this centering assumption essential, or is it made simply for the sake of simplification? In other words, we can use other Gaussian process non-centered.
Yeah, I don't think it's a particularly crucial assumption. And one of the reasons is that at the end of the day, you can, if you consider non-centered, at least for B, let's say for the bias, you can put this non-centering inside the sigma, right? So you can put the sigma, you can just put this non-centering inside the sigma.
Okay.
Or for W, I think one has to be careful. I think one has to be a bit careful about this. I think the centering plays, however, a role. I mean, you can truly, at least heuristically, show that. I think one can overcome this by being careful. At the end of the day, what you have is an iteration, at least heuristically, is an iteration of the central limit theorem. So as soon as you put yourself in a situation in which the central limit theorem applies, and of course the central limit theorem applies with the non-center random variables, then you can reproduce the proof, right?
Okay.
So I cannot, on the top of my head, exactly see how to regulate the parameterization of the centering of the of the mean, but it is possible. I think it doesn't change very much in one way things properly. Yes. I don't think it's essential. Yeah.
Okay. There is another question in the chat. The question is, which structural assumptions on the activation function, weights, and input dimension are needed for the optimal Stein and total variation bounds?
Rafik, why don't you give the
maybe he cannot.
Question.
Dr. Mohammed Mudassir, can you ask your question?
Hello, Professor.
Hello.
I hope you are fine.
Sorry?
I hope you are fine. I wrote a question.
Yes.
In the chat box. You took the simple structure in which you just took two inputs like x1, x2, and similarly with two hidden layers, and the last one was related to output. I want to know which structural assumptions on the activation function weights and input dimensions are needed for the optimal Weierstein and total variation bounds.
So the optimality of let's say so let's say what I wrote here. So this is the finite dimensional setting, and what I say here. So I wrote in a very vague way non-degeneracy assumption. So what non-degeneracy assumption means? It means that these KL functions that appear in this statement. So not just the limiting one, but the KL, each one of them has to be invertible, right? It has to be non-singular. Okay, so if we forget about derivatives, so I said here I take the liberty of taking derivatives, right? So if you forget about derivatives, that is, if you just take the network, this assumption is rather generic. That is, it is sufficient to have some non-trivial assumption of C of B by saying it is non-zero. So there is a way of adjusting CB and CW in a sort of generic way, such that this assumption is always verified. Now, if you move to derivatives, as far as I know, the situation is a bit of on a case-by-case basis. One has truly to work through the definition. I do not think, and at least I did not do it, I did not perform a thorough analysis of that. So I think your question is particularly relevant whenever derivatives are involved. But if we
took a big graph, like you have chosen a very small graph in which you just took some vertices and you have applied your methodology. If we took a very big graph, thus the same results, the same methodology holds your results?
Yes. The results I'm given here are independent of capital L. They hold for every L. And of course, L is in the constant here, but the speed of convergence is independent of L, right? So this is an important point. This is a very good question, because it means that if one is interested in the speed of convergence to the Gaussian, and it means that if you can modify however you want the depth of your network, and this becomes is invariant, right? The sort of invariant of the network. Yes. So everything is independent of L. Yes, absolutely. And even
my just last question is this: what are the other applications where we are using this methodology? What we can achieve in our real life when we apply this methodology? This is related to graph theory, maybe. When we apply this method in our real life, so what kind of advantages we can get?
So do you say outside machine learning, right? So we don't care about neural networks anymore, right?
Yes.
That's good. This is good. This is very good. Right. So what I would like to say is the following. So now there is one point that I put forward very much. I told you everything that I was describing is given by the fact that these objects are conditionally Gaussian, right? Conditionally Gaussian is some sort of a very strict requirement. But actually, this is not the case completely. The fact of being conditionally Gaussian simplifies our lives. But what is truly important behind the scenes, and this is the smooth transformations or relatively smooth transformations of Gaussian noises. And you can see everything that I've told you as a derivation of a much larger collection of results that combine with Stein's method with the Malyavin calculus. And then in this case, the applications are countless. For instance, we have a number of applications to random fields. So the picture that I put at the very end here, not here, but here. So this is the Gaussian field that appears in differential geometry. There have been applications to that in computer science, statistics, estimation, functional estimation, cosmology. It is a very general framework. What seems to be restrictive here is the conditionally Gaussian structure. But this conditionally Gaussian structure can be replaced by something much more general. And then the results become truly, truly general and can be applied to a number of situations. So in particular, statistics, cosmology, algorithm analysis, or medias. And of course, stochastic geometry, right? Where random graph theory or tessellation or percolation also.
Okay, thank you, Professor, for your precise answers.
No, thank you for the questions. They were very good, very nice questions. Thank you very much.
Hello.
Yes, please.
Thank you, first of all, for this nice presentation, Professor. I have one small question that there are other class of model, as you know, called ELM, Extreme Learning Machine, and then the new variant, Deep Extreme Learning Machine, DELM. And in those type of models, the random weights are actually there. So it's like pure randomization. We start randomizing the weights and the bias.
Okay.
But unlike this deep neural network, those random hidden weights and biases are not trained afterward. So my question is, can we use the same methodology of yours like doing this Gaussian scaling, and initialize the weights of ELM. So can the theory be like applied in this sense, or any benefit of using the Gaussian weights in this ELM?
Yeah, so I'm not completely familiar with this family, but what I can tell you is that as soon as you have a function, as long as you have a function of Gaussian weights, then and you have some dimensions, so that is you can let the number of Gaussian, the dimension of the Gaussian noise diverge to infinity in some form, then the methodology is general, the methodology applies. Then one has to see whether this is relevant for the models themselves. So in our case, it is relevant because of this MTK phenomenon. Basically, everything about the training is decided at initialization, right? So then studying the large-scale structure of the model initialization, because of MTK, tells you many things about the behavior of the model after the training. So I would say that mathematically, as soon as you can let the number of Gaussian objects diverge in some form, then the methodology applies almost automatically. I'm not sufficiently familiar with this class of models in order to say whether this is significant or relevant for the application of the models themselves. What I can tell you is that some version of this methodology applies to another family of models that are the ResNet models, that are recursive, in which the natural thing is to let the depth go to infinity in such a way that you see differential equations or ordinary differential equations appearing as a scaling limit. So for those models, this kind of techniques are very relevant. So my answer is therefore everything is possible, and then I should be more familiar in order to see whether this is truly an important information, an important step in order to understand the behavior of those models.
Thank you.
Yeah.
I have another question. You assume that all Ni tend to infinity. Sorry.
I assume what?
You assume that all Ni tend to infinity, and 1 to NL goes to infinity.
Yes.
Okay. Could we instead allow some Ni to be, for example, equal 1? And in this...
could we fix 1 and 1? Could we?
Yes. For a certain I, and I equal 1. And in this case, could we decompose the graph in two subgraphs where the node X and I would play the role of the output of the first subgraph and the input of the second?
Sure. It is this. You are right. It would be like that. So I think that, one should do the computation, but I think that it would be, we would obtain at the limit something which is even the limit, right? Not just for fixed, but the limit will give us something which is conditionally Gaussian. It will be some sort of a Gaussian object with a Gaussian Gaussian-based covariance matrix. So if you fix one dimension, you don't let this dimension go to infinity, then you basically will have a set of weights that are not do not scale like the central limit theorem. We just stay fixed, and then I think we will have exactly the phenomenon you are mentioning. You have some sort of a nesting of networks, and so which give us some sort of a macro networks nested one into the other, and I think it is exactly what would happen. Yes.
Okay.
Yes.
Another question: do you expect similar quantitative bounds to hold under non-Gaussian initialization?
Yes. The answer is yes, because Lucia Celli did it. So I didn't put the results. So, but Lucia has a 100 pages, one single author paper, where she proves. So she deals with non-Gaussian weights, and she has she does just the finite dimensional case, which is horrible enough from a technical point of view, and she obtains bounds, I think, in a convex distance, and the rate is the square root of n. Right.
Okay.
But what she has an incredibly good control of the constant c here, which means that in a non-Gaussian paper that also covers the Gaussian case, she is able to make not only n go to infinity, but L, that is the depth of the network, go to infinity at the same time, which is a much more complicated situation. So the answer is that in a non-Gaussian case, the best we can do is the square root of n, but the techniques allow to let L let L move to infinity with n. And it's sort of a trade-off that I like very much. That's why I think it's a good trade-off. I'm ready to sell some n in order to gain some L.
Nabil, you have a question, Nabil Gmati?
Yes, thank you, Rafiq. Okay, I have a very naive question, but perhaps I missed something in the lecture. But here you extract some properties, some bounds for a neural network, a deep neural network. Did these properties allow to optimize the hyperparameters of a neural network, or the data set to obtain for the same precision of the result, or it's just quantitative properties to understand how a neural network works?
Okay, so this is a good question, and I think the answer is no. No, because of the nature of the bounds in the following sense. So I think there is so it would be, let's say, one could expect a priori, before performing any computation, one could expect that the bounds, for instance, the speed of convergence, let's say in this bound here, for instance, and the bound should be n to some power, and that the power depends on the hyperparameters of the network. For instance, depend on L, depends on the regularity of sigma. I think this is what you're thinking about, right? This
exactly, yes.
Yeah, right. And so if it was the case, then this would be an extremely important information, because it tells you that if you're truly interested, and one of the criteria for you in order to build a network is the speed of convergence, then you should optimize the architecture in such a way that the speed of convergence is as fast as possible. So if I'm not wrong, in the jargon, this is a name, this is hyperparameter transfer. It means that you have a big network, you want to build a smaller one, and you want to keep all the nice features of the bigger the network on the smaller network. Now, these results are sort of negative results in the following sense, that all these results that concern the speed of convergence to the Gaussian, that in principle could be used in order to determine some form of hyperparameter transfer, cannot, because they have a universal nature. They end at n1/8. Actually, simulations I did show tell you that maybe it should be n to the power 1/4, but these are all independent of the hyperparameters. So I think that by their very nature, they cannot be used in this way. I think they can be used in this way if one puts L in that is the depth of the network in the picture. I think in general people tend to grow both n and L at the same time, and I think in this case there is a much sharper dependence on the architecture of the network. And actually, I think that the relevant parameter should be the ratio L/n, which is known as the effective depth of the network. So if one takes the effective depth of the network as a parameter, then I think the speed of convergence would depend on the hyperparameters, and then this hyperparameter transfer could become something more relevant. But for the moment, no, because 1/8 is 1/8, 1 is 1, and yeah, so it's not directly usable in this direction. But this is an excellent question, actually, that tells you somehow the limit of these results from an operational point of view. Absolutely.
Thank you very much.
Yeah.
Other questions, please? If not, we have to thank again Professor Giovanni Peccati for this nice talk. And see you next week avec another talk of Professor Eli Sedmiller. Thank you.
Thank you a lot.